Now we're going to get to the area under plot or under graph for continuous variables. Now remember, with a discrete, we made the width of those little bars 1. That's discrete variables. They stand on their own. Now for continuous data, though, by definition, we can continuously divide it smaller, 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 and in theory at least there should be no infinite limit. Now, what can we do? How can we solve this problem? Because we still want to deal with area. Can we draw an ultra thin little bar, tiny little base, tiny little width? We really can't do that, because any one you draw, I can cut in half as well, by definition. So remember, although that is theoretical, practically it's not really so. Remember, we talked about the blood pressure, that if I had an apparatus that was could do infinitely fine measurements, I could work out a systolic blood pressure of 120.555, 6, 7, 8, 9, or if I were dealing with very large numbers like the white cell count in human blood. But practically speaking, we can make those bars smaller and smaller, and eventually we're going to end up with a bar with a width of 0, and then we can't work out area anymore. So what do we do? Fortunately, mathematicians to the rescue, as per usual. And you see the graph there, it's a negative x minus a squared, a nice little graph there, a parabolic curve there, and we can work out the area under the curve. We needn't have a special shape like a square or a rectangle. That very smooth curve there, we can work out the area under the curve for that between two limits. Integration is quite easy to do. Now, the mathematics behind statistics is going to draw this beautifully symmetrical normal curve, Gaussian bell-shaped curve for us, and it can work out the area under the curve for that. Now you can ask yourself, how would this really work? Can I just draw a line up from the x-axis and just read off the probability? Remember, that's not how a p-value works. That little bar has a width of 0 in essence. So we can't just look at one specific value. We do something different. I want to remind you, when we rolled the dice, we said what was the probability of rolling an 11 or a 12. So we added those values, and we're going to do exactly the same with a continuous variable. We're never going to ask what the probability of finding one value is. We're going to color in an area under the graph for some distance from a spot out to one of the two sides, and we're going to calculate that probability. We're going to find our value somewhere in there, and then say if it's more or less than, say, 0.05, that was our magical value. Now we construct that little graph, or at least the mathematics or the program that you use is going to construct that little graph so that the whole area is still 1. It's going to be same as we had with the rolling of the die. The total probability has got to equal 1. It's got to add up to 1. And this is what's going to happen behind the scenes when you do the math. If you chose 0.05, now the graph that you see there, that's not really to scale, but it is going to decide where to make the cutoff so that you see the darker area there, the darker blue area, where that would represent 5% or 0.05 of the total area under that curve. The value that is found by doing research is then going to fall either within those limits, and we can work out the p-value, the probability for that, the area under the curve, but we would say it is less than 0.05. Having found that result for that research at a probability of less than 0.05. So it's going to convert all the differences in means, or the means of a group, it's going to convert that to some value on the x-axis, and it's going to fall either within that 0.05, or it's going to fall outside of that, and we can actually work out that area under the curve. Now, you've seen me draw little curves and everything was on the one side. Remember, most of the time that's not how we're going to do it. We're going to do this. We're going to split the 5%, the 0.05 up in 2 into 0.025, 2.5% on either side. And our values are going to fall on either side of that, and we're still going to calculate an area under the curve. So that's how it works. It's an area under the curve. It falls between different limits, and the results that are found either falls within those areas, or it falls outside of a p-value of less than 0.05 or p-value more than 0.05.